E or ds. Okay. So phi is equal to vector E dot S or ES cos theta. Right? Any doubt in this?
No, ma'am.
Okay. Let's move to the next slide. So here we have MCQs. Electric flux is defined as the number of field lines passing through the surface.
Normally.
Normally is the correct answer. Second, electric flux is an elementary area defined as the dash product of area
Vector
and
product.
scalar product. Beta. It is vector
Product.
ds. No, it is a scalar product. Okay. It is a scalar product. Okay. Before doing this numerical, let's consider a situation. What if a surface is placed perpendicularly to the direction of electric field?
Ma'am, the net electric field would be 0. Flux would be 0, right?
See, we have this surface. We have this surface.
We have this surface, ma'am.
Surface is placed. This is the surface we are taking. This notebook we are considering as surface. And this surface is placed perpendicularly to the electric field. So this is the direction of electric field.
Yes, ma'am.
And this is the area element. Where do we take the direction of area vector?
Normal to the surface, ma'am.
Normal to the surface. So direction of electric field is this, and direction of area element is the same. So they both are pointing in the same direction. So what is the angle?
Therefore, make the angle 0 with them.
It is 0 degree. So and the value of electric flux
is ES cos theta. ES, ma'am.
So cos 0 degree is 1. So value of electric flux is ES. So maximum number of lines can pass through the surface when it is placed perpendicular to the electric field. When a surface is placed perpendicular to the electric field, then maximum number of lines, you can see, maximum number of lines can pass through it. And hence electric flux is the maximum. And if we place a surface parallel to the electric field, then electric field is in this direction. Surface is also like this, parallel to the electric field, then what is the direction of area vector? Normal to the surface. It is always normal to the surface. Direction of area vector is normal to the surface. Direction of electric field is this. Electric field is horizontally, acting horizontally, and this area vector is acting vertically. So what is the angle between electric field and area vector in this case? 90 degree.
90 degree, and we know that cos 90 is 0. The total electric flux is 0, ma'am.
Yes, cos 90 degree is 0, and hence the electric flux is 0. Okay. And if you place the surface at an angle, then if you place the surface at an angle with the electric field, then this is the electric field, direction of electric field. My arm indicates the direction of electric field, and this book is the surface. And the angle between these two is theta. Now, what is
theta
the
degree?
ES cos theta. It's
ES cos theta.
Okay. This is how we find the electric flux. Next, we have a question. Consider a uniform electric field. E is equal to 3 into 10 raised to the power 3 I cap Newton per coulomb. So you can see this I cap. So electric field is pointing in next direction. What is the direction of electric field? X direction. Because with vector E we have unit vector I cap. With vector E we have unit vector I cap. Okay, so I cap क्या है? Unit vector होता है along x-axis. So it indicates the direction of electric field along x-axis. Now we have to find electric flux of this field through a square of 10 centimeter on a side whose plane is parallel to YZ plane. So plane is parallel to YZ plane. See, if this electric field आपको given है, electric field is 3 into 10 raised to the power I cap Newton per coulomb. So you can see that we have I cap here, so it is along x-axis. Electric field is along x-axis. Now we have to find the flux of this field through a square of 10 centimeter on a side whose plane is parallel to YZ plane. So we have a square. This is electric field. We have uniform electric field. Admit kar liya to fir aa jayega. We have uniform electric field and we have a square here. It is placed perpendicular to the electric field. Okay, and side of square is 10 centimeter. So this is the electric field and this is the area element that we have. So what is the direction of area vector? Yes. Okay, so this n cap is the direction of area vector. This is how we write. So vector S is the area and vector S can be written as area into n cap. So you can see both the electric field and the area vector, they are pointing in the same direction. So what is the angle between these two? What is the angle? Angle is 0 degree. Angle is 0 degree. किससे नहीं हुआ ये? आपसे नहीं हुआ पीछे? आपसे नहीं हुआ? आपसे नहीं हुआ? स्क्रीन दिख रही है, विजिबल है? ठीक है? Electric flux is vector E dot vector S. This is how we write electric flux. Electric field intensity into area. It is the dot product of these two vectors. And this can be written as magnitude of electric field intensity, magnitude of area into cos theta, and theta is the angle between electric field intensity and area element. This theta is 0 degree in this particular case. Now we have side of the square as 10 centimeters. So we can find area of the square. So area of the square is side square. Okay, side square. So it is in centimeter. So first we need to convert this into meter. So in meter, it is 10 to the power minus 1 square meter square. So answer is 10 to the power minus 2 meter square. You simply have to put the values here. Value of electric field intensity, it is 3 into 10 raised to the power 3. Value of area, it is 10 to the power minus 2. And cos theta is cos 0 degree. Cos 0 degree is 1. So we will get 30, because this is electric flux. What is the unit of electric flux? Newton. See, unit of electric field intensity is Newton per coulomb. Unit of area is meter square. Now tell me the unit of electric flux. Newton meter square per coulomb is the unit. Okay. Next, second part. B. This is A. Now we are doing B part. What is the flux through the same square if the normal to its plane makes an angle of 60 degree angle with the x-axis? Normal to its plane means, so we have electric field intensity pointing in this direction. Okay. And see, normal to its plane. Square if normal to its plane. What does it mean? So if the square is held in the electric field like this, then normal to this area would be in this direction. So this is n cap, this is S, and this is electric field. Now tell me the angle. The angle is given, it is 60 degree. Okay. Find electric flux. So electric flux pi E, again it is ES cos theta. So you simply have to put the values here. E is electric field intensity, its value is given. S is area, it is 10 to the power minus 2. And cos 60 degree we have. So put the value of cos 60 degree is equal to sin 30 degree. So 3 into 10 raised to the power 3 into 10 raised to the power minus 2 into 1 by. Answer is 1.5 into 10, or we can write 15 Newton meter square per coulomb. Okay, this is how we can write. Any doubt in this? Yeah, Gauss's law. This we had covered in the previous class only. What is it? Let's revise it. Gauss's law says that total electric flux through any closed surface is 1 upon epsilon naught times the total charge enclosed by that surface. Okay, so electric flux is Q upon epsilon naught, where epsilon naught is the permittivity of free space. Okay, so we consider a closed surface enclosing the charge Q, and electric flux is charge inside the closed surface divided by permittivity of free space. And what is the value of permittivity of free space? 8.85 into 10 to the power minus 12 unit coulomb square per Newton. Batao, what is the unit? Coulomb square per Newton per meter square. And what is the, how do we write electric flux? By the definition of electric flux, because electric flux is number of field lines crossing an area. So we can also write electric flux as closed integral of vector E dot ds. So by comparing these two, we can write electric flux as phi E is equal to closed integral of vector E dot ds is equal to 1 upon epsilon naught times the charge. Okay. So we had done the proof in the previous class only, where we had taken a point charge Q, we had taken a spherical surface for that point charge, the Gaussian surface, and then Gaussian surface of spherical surface of radius r. Then we can write electric field intensity at any point at a distance r from the charge as kq by r square. This we had covered. फिर उसके बाद क्या करते हैं हम एक एरिया एलिमेंट कंसिडर करते हैं ds and then we write d phi as vector E dot ds. इसमें किसी को डाउट है? मयंक को है. You were absent in the previous class. तो अब वो कैसे आएगा ये? ठीक है, तो d phi is vector E dot ds. Then we put the value of vector E, है ना? Vector E की value put करोगे, it is kq by r square. Put the value of vector E here, you'll get d phi as this. Now we will integrate it to get the total flux. To find the total flux, we will integrate it. All the quantities are constant here, right? And ds on integration gives the
Yes.
area of the sphere, the spherical shell. It's 4 pi r square. Now we will cut it. 4 pi cancel. R square cancel, and we are left with q upon epsilon naught only. Yes. Where do we use Gauss's law? We can find electric field intensity where there is symmetry in charge distribution, right? This we had discussed in the previous class, and is used to find total flux associated with the closed surface. By applying Gauss's law, we can easily find out the electric intensity due to various kinds of charge distribution. Now we have questions based on this. In Gauss's law, the total electric flux over a closed surface is equal to, tell me the answer.
1b, ma'am.
Yes, it's B 1 upon epsilon naught times the charge enclosed within the surface. Next question. We have a point charge of 2 microcoulomb. It is at the center of a cubic Gaussian surface 9 centimeter on H. What is the net electric flux through the surface? Find the net electric flux.
मैम ये बहुत आसान क्वेश्चन है.
बिल्कुल इजी है, करो फटाफट. Charge is given. Charge is 2
Surface भी
coulomb.
और परमिटिविटी की वैल्यू भी हम लोग जानते हैं कितनी होती है ना, 8.5 into 10 to the power minus 12.
Yes, epsilon naught is 8.85 into 10 raised to the power minus 12 coulomb square per Newton per meter.
अब गॉस लॉ के फॉर्मूले से निकाल देंगे.
Yes. So electric flux is Q upon epsilon naught. Arshia, please write this. Put the values and get the answer. Charge is given. See, here we don't need this value. We don't need this value because we have to find net electric flux, and net electric flux depends upon the charge enclosed. Net electric flux depends upon the charge enclosed. So we only need the value of this charge, which is 2 microcoulomb. It is given to us. So first we will convert this microcoulomb into coulombs, and then we'll write the value of epsilon naught. Put these two values here, you'll get the value of electric flux. Solve this for phi. वापस करवा दूं. देखो आपको चार्ज दिया हुआ है और आपको ये बताया हुआ है कि क्यूबिक गॉसियन सरफेस है 9 सेंटीमीटर ऑन एच. इट इज नॉट रिक्वायर्ड बिकॉज हमारे लिए मैटर करता है कि किसी भी आपके क्लोज सरफेस में चार्ज कितना एनक्लोज्ड है. दिस इज व्हाट वी नीड. ठीक है, टोटल चार्ज एनक्लोज्ड बाय अ सरफेस इज रिक्वायर्ड. So we only need this. So because charge is given and we know the value of permittivity of free space and electric flux is Q upon epsilon naught.
Done, ma'am.
right?
Answer is
So we simply have
2.26
to
into 10
put
to
the
the
value.
power 5.
Okay. We simply
Then
have
m
to put the
square
values
symmetry.
and solve it. Yes. No. No. What will you get? 2.26. Yes, Ram, give me the answer.
The final answer of this question is 2.26 into 10 to the power 5 Newton meter square C negative.
Yes, Newton meter square per coulomb. This is the final answer. Okay. Applications of Gauss law. So first is we will find electric field intensity due to a line charge. So line charge is, you can see here that charge is uniformly distributed on this line element. So let the length of this wire or the line element be L. L is the length of the wire or the line element, and this charge is distributed uniformly everywhere. Because here we have uniform distribution of charge, so we can consider charge density, linear charge. So Gaussian surface should be, it should be cylindrical in shape, because everywhere on the cylinder you will see either the electric field intensity is constant or it is zero. The Gaussian surface should be selected in such a way that either the electric field intensity is zero or it is constant on the surface. So for this line element, we will choose cylindrical Gaussian surface of radius r, let's say. Okay. If we consider a small area element ds on the Gaussian surface, then everywhere you will find this area vector is pointing in the perpendicular direction on the cylindrical surface. So n cap is everywhere, you will see that it is perpendicular. Even at the edges it is perpendicular. On the curved area it is perpendicular. Everywhere it is perpendicular. Okay. So this is the area vector, direction of area vector. Listen to each and everything, each and every step very carefully. This derivation is very important. Can be asked in your exam. Okay. Now, because we have a line element, it consists of positive charge, and electric field intensity points away from the positive charge always, every time you can see. For a positive charge, electric field intensity is away from the positive charge. So on the curved surface, we have this electric field intensity vector. You can see r cap here. It is pointing perpendicularly in the same direction where n cap is. On the curved surface, both r cap and n cap, they are pointing in the direction. But if you look at the edges, then r cap and n cap, they are perpendicular. On the curved surface, these are parallel. At the edges, they are perpendicular. Okay. So we can write electric flux as closed integral of vector E dot ds as per definition of electric field, and it is equal to Q upon epsilon naught using Gauss law. Okay. So lambda is a linear charge density. So lambda is Q by L, charge per unit length. So we can write charge as lambda L. Any doubt?
No, ma'am. And similarly, we can now.
Yes. Now we can
Ma'am,
vector E dot ds. Yes. At the edges we have, you can see at the edges, r cap
2
and
pi
n cap
r
perpendicular.
into 2 pi r.
Please wait. At the edges, r cap and n cap are perpendicular. R cap is pointing in this direction and n cap at the edges is pointing outward. So angle is 90 degree. Dot product of two vectors. When we have angle between the two vectors is 90 and we're taking the dot product, then cos 90 is 0. So it is 0. And if you look at the curved surface, then on the curved surface of the cylinder, this r cap and n cap, they are parallel to each other. So when we take the dot product, we'll get 1 because cos 0 degree is 1. Okay. So at the edges, it is 0. R cap dot n cap is 0. And on the curved surface, it is 1 because when we take the dot product of two vectors which are parallel, we always get, we simply multiply the unit vectors because we have unit vector, their magnitude is 1. Okay, the magnitude is 1. So magnitude of r cap multiplied by magnitude of n cap and cos 0 degree. This is how we write. So 1 into 1 into 1 is 1. Okay. Because this electric flux is vector E dot ds, and vector E can be written as E dot r cap and ds can be written as ds dot n cap. So we can write E close integral ds. Okay. Now at the edges, because r cap dot n cap is 0. Look at this. Look at the cursor. This r cap dot n cap is 0 at the edges. and therefore electric field is also 0 there. Okay, because r cap dot n cap is 0. They are perpendicular, na? So electric field is 0 there. This electric flux is 0 there. And on the curved surface, r cap and n cap, they are pointing in the same direction. Angle between them is 0 degree. And therefore, this r cap dot n cap is 1. R cap dot n cap is 1. So when we'll put the value here, we get E close integral ds. And close integral ds is the curved surface area of the cylinder. Because we are considering the curved surface, we'll take area of curved surface only. Edges will not be included because at the edges we have electric flux 0. So edges we will not include. We will only include the curved surface. Okay.
Yes, ma'am.
So E into 2 pi RL. 2 pi RL is the curved surface area of the cylinder. Now consider this as first equation, this as second, and this as third. Now compare these three, 1, 2, and 3. So phi E is either we can write close integral of E dot ds or we can write Q upon epsilon naught. So close integral of E dot ds is E into 2 pi RL. And this Q upon epsilon naught, Q is lambda L. So lambda L upon epsilon naught. So equate these two, cancel this L, and you will get your electric field intensity as lambda upon 2 pi epsilon naught R. So here in this particular case, this electric field intensity is inversely proportional to R, not R square. Usually we have electric field intensity inversely proportional to square of R. But in this particular case, we have inversely proportional to R. Okay. Of May, 2 chapters आएंगे. 15 अप्रैल. आज क्या है? तो बस आज चैप्टर आज यही आएगा ना, बस एक ही. हाँ तो बस ठीक. कुछ चक्कर नहीं है. अब करवा के छोड़ूंगी मैं. मैंने आपके चक्कर में क्लासेस रखी थी कि मुझे था कि आपका एग्जाम 15th को है तो पहले उससे चैप्टर कंप्लीट करेंगे. Okay, next question. The electric field intensity at a point due to line charge distribution at a distance r is directly proportional to. Is directly proportional to. बताओ. 1 by r. Next
1
question.
by R.
A Lohr meter is given. Charge per meter means charge per unit length is given. Find the electric field at a distance of 0.2 meter from it. These are the options. Answer is 1800 Newton per coulomb. Volt per meter. Lambda is given, it is 2 in 10 power minus 8 coulomb per meter. This is coulomb per meter. And R is given, it's 0.2 meter. So we will put the values here in the formula of electric field intensity. Two lambda upon 4 pi epsilon naught. We have multiplied and divided by 2 because in this way we'll get 4 pi epsilon naught in the denominator, which we can solve easily because 4 pi epsilon naught की value हमें पता है, it's 9 times power 9 ना. 1 upon 4 pi epsilon naught. So we can directly put this value here, and 2 into this lambda is 2 into 10 power minus 8 coulomb per meter, and R is 0.2. See, we have multiplied and divided this by, we have multiplied numerator and denominator both by 2 because we want 4 pi epsilon naught in the denominator because it's easy, na? 1 upon 4 pi epsilon naught is 9 into 10 power 9. So ये intentionally किया है, इसको काटना नहीं है, ये खुद ही multiply किया है because it is easier to put the value of 1 upon 4 pi epsilon naught instead of putting the value of pi and this epsilon naught here, right? Yes. Becomes difficult. Okay. Answer is 100 joules per meter. Should I move to the next slide?
Yes.
मैम टू मल्टीप्लाई करे बिना भी.
हाँ, मल्टीप्लाई करे बिना भी हो सकता है, बट उस केस में फिर आपको पाई की वैल्यू पुट करनी पड़ेगी, वो लेंथी होगी.
हाँ मैम, टाइम ज्यादा लगेगा ना.
टाइम ज्यादा लगेगा.
R2 दिया हुआ है.
R is 0.2. अगर हो रहा है इजीली तो कर लो, अच्छी बात है. ठीक है. Should I move to the next slide?
Yes मैम.
अभी जो आ रहा है ना वो न्यू आ रहा है. आप अभी फ्रेश पढ़ रहे हो, अभी तक आप पुराने ही लगे हुए थे करने. ठीक है. नई वाली चीज तो पढ़ना स्टार्ट कर रहे हैं हम, जो आज हम शुरू करेंगे स्फेरिकल चेयर. बहुत ध्यान से सुनोगे और हर डेरिवेशन को मैं एक्सप्लेन करूंगी, आप लिखोगे नहीं और बाद में आप अपने आप लिखोगे बिना देखे। मैं इसको बंद कर दूंगी और फिर आप लिखोगे, ठीक है? क्या क्या So electric field due to a charged spherical shell. Because we have a spherical shell and it is hollow from inside and it is charged. So all the whole charge will reside on its outer surface. वैसे भी if we have a conductor and we give charge to a conductor, then charge goes to the outer surface only. No charge resides inside the conductor. This we had discussed in the first or second class of electric field, right? This chapter. So consider a spherical shell of radius r and a charge q. Let us find the electric field at a point P at a distance r from center O of the shell. Okay, so we have a spherical shell of radius r and we have given the spherical shell charge q. And now we are going to find electric field intensity at a point P. That point P is an arbitrary point. We can locate that point P anywhere around the spherical shell. We can place the point P outside the spherical shell. We can place the point P on the spherical shell. We can also move that point P to inside the spherical shell. Okay, because now in this case, charge is uniformly distributed and it is the spherical shell. So we will consider surface charge density. Surface charge density is denoted by letter sigma and it is charge per unit area. What is the, how do we find the surface area of a spherical shell? Surface area of spherical shell is 4 pi r square. Surface charge density will be q upon 4 pi r square. Sigma is q upon 4 pi r square. Okay. And therefore q is 4 pi r square into sigma. Sigma is the surface charge density. It is charge per unit area. Okay. So we can write charge in terms of surface charge density. So when P is outside the shell, we have this point P. This is the center and this point P is outside the shell. This is the spherical shell and point P lies outside the spherical shell. Distance from the center to the point P is, let's say, r, small r. We will consider a Gaussian surface which passes through the point P outside the shell. See, this solid line indicates the spherical shell that we have. Now, around this spherical shell, we are considering a Gaussian surface. Okay? And this Gaussian sphere passes through the point P. Because we are going to find electric field intensity at point P, so we will consider Gaussian surface which passes through point P. Okay? Any doubt? This spherical shell is uniformly charged. Okay? And radius of this spherical shell is r. Charge given to this spherical shell is, let's say, q. So we can easily find surface charge density for this spherical shell. So surface charge density is denoted by sigma. It is equal to charge per unit area. Okay. So we can write charge in terms of charge density as 4 pi r square sigma. Okay. Now we have to find electric field intensity due to this uniformly charged spherical shell. So we can find electric field intensity at 3 different positions. Outside the shell, we can find electric field intensity at this point. We can also find electric field intensity here on the spherical shell. We can also find electric field intensity inside the spherical shell at any point inside the spherical shell, somewhere here, here. So these are the 3 different locations, location 1, location 2, and location 3, where we'll be finding electric field intensity due to this uniformly charged spherical shell. Okay. If we have to find electric field intensity at this point, 0.3, then we will create a Gaussian surface which passes through 0.3 because this is a spherical shell. So Gaussian surface is also spherical for this, right? So we can construct a Gaussian surface like this outside the shell. Another sphere which encloses the given spherical shell. Okay. Similarly, if we have to find electric field intensity at this location, then we already have a spherical shell. We'll construct a Gaussian surface here only. If we have to find electric field intensity inside the spherical shell, then we can construct a Gaussian surface here, which passes through this point. So where we have to find the electric field intensity, there we take the Gaussian surface. Now we are going to find electric field intensity outside the shell. Okay. Field outside the shell. कैसे find करेंगे electric field intensity outside the shell? See, close integral of vector E dot vector ds is equal to q upon epsilon naught, right? So here in this case, both vector E and the area vector, they are pointing in the same direction. If this point P lies outside the shell, then we will construct a Gaussian surface. आ गया राम? We will construct a Gaussian surface outside the spherical shell only. Okay. We will construct a Gaussian surface outside the shell. So we can take any area element on the Gaussian surface. Okay, we can choose any area element on the Gaussian surface and this area element is ds. So area vector and vector E. You can see this vector E is away from the positive charge and area vector is pointing in the same direction where the electric field intensity is pointing. Because they both are pointing in the same direction. So we have theta equal to 0 degree. Theta is 0 degree. So we can write EDS cos 0 degree. Okay, close integral, and this is equal to q upon epsilon naught and cos 0 degree is 1. Okay, now E close integral ds is equal to q upon epsilon naught. So this represents the total area. This represents the total area. So total area means area of the spherical shell that we have assumed. Gaussian surface. Area of the spherical Gaussian surface. So let's take the distance from the center to the surface as small r. Now tell me the area of Gaussian surface. It's 4 pi small r square. E into 4 pi small r square is equal to q by epsilon naught. So this implies E is equal to q upon, we can write this 4 pi epsilon naught together and r square. Okay. So this is the electric field intensity outside the spherical shell. And close this in bracket, in box, and close your expression in the box. Now you can see that in this particular case, this electric field intensity is inversely proportional to square of r. Okay. So if I want to draw a graph, then E versus R, I'm going to draw. This represents distance from the center and this represents the electric field intensity. This represents the distance from center, distance from the center. And this represents electric field intensity along this axis. So we can take this as R because this R, distance R can be changed. We can move this point P. So wherever we have this point P, there we'll draw the spherical shell. So this is very flexible. Okay. So if at the center we can consider 0. So on the surface, this small r is equal to R, right? On the surface, small r becomes R. If we consider a point P here, then Gaussian surface would be here only, and then small r becomes R. And if we go inside the spherical shell, then small r is here, small r is less than R. And on the surface, this small r is equal to r. Outside the surface, this small r is greater than r. So it depends upon the location of point P, where this point P is. Because where the point is, there we have the spherical shell. And where we have the spherical shell, accordingly, we'll have the radius of the spherical Gaussian surface. Spherical Gaussian surface, right? Any doubt here? So if I want to draw the the graph between this electric field intensity and r square. So this is the case when our r is greater than r. And here we have r less than r. So we'll start from here and it goes like this because it is inversely proportional. So E is decreasing with the distance. Hai na? E is decreasing with square of distance, right? So we'll get the curve like this. E is decreasing with distance, we can see it is clear. Okay. Now, let's consider another situation. At a point on the surface of the spherical shell. At a point on the surface of the spherical shell. If this point P lies on the surface, then our small r is equal to capital R. We'll draw the Gaussian surface where the point is. Now we want to find the electric field intensity on the surface of the spherical shell. So R becomes capital R. Okay. And so electric field intensity becomes, tell me, it is E closed integral of ds is equal to q upon epsilon naught. This is we write like this. So this closed integral of ds is, this time it is 4 pi capital R square is equal to q upon epsilon naught, right? So this implies E is equal to q upon 4 pi epsilon naught R square. Now, when we consider this point P on the surface, so this you can write this Q, surface charge density, in terms of surface charge density. So this Q can be written as, why are we writing like this? Why are we writing like this? We कैंसिल हो जाएंगे, थोड़ा सा हमें और सिंपल सा एक स्ट्रक्चर, एक फॉर्मूला मिल जाएगा. Because on the surface we have charge present, so we can write charge in terms of surface charge density. तो 4 pi से 4 pi cancel हो जाएगा and r square से r square cancel हो जाएगा and we are left with this sigma upon epsilon naught. Now you can see that on the surface this electric field intensity does not depend on r. It is sigma upon epsilon naught. Epsilon naught is a constant. Sigma for this particular case is a constant. Okay. So electric field intensity has the maximum value on the surface. Electric field is maximum on the surface of spherical shell. E is maximum. Okay. So this is the maximum value that we'll have. It is equal to sigma upon epsilon naught. When r is equal to r is equal to r. When r is equal to r, then electric field intensity is sigma upon epsilon naught. Okay. Clear? Should I erase this part? This reason? I'm going to erase it. Okay. Now inside the shell, field inside the shell. field inside the shell. How will we find field inside the shell? Inside the shell means when R is less than capital R. When R is less than capital R. Is there any charge inside the spherical shell? No, there is no charge. No charge implies no electric field. चार्ज ही नहीं है तो इलेक्ट्रिक फील्ड कैसे होगा? ठीक है? No charge implies means no electric field is there. So electric field intensity is 0 inside the spherical shell. But what if we have a non-conducting spherical shell then? For non-conducting spherical shell, field inside the shell is not 0. Solid sphere. For non-conducting solid sphere, field inside the solid sphere, non-conducting solid sphere is not 0. Because in that case, we have charge inside the solid sphere. That's for non-conducting. But here we have conducting charged spherical shell. Whether it is a solid sphere or a spherical shell, charge always resides on the outer surface of a conductor. कंडक्टर में चार्ज हमेशा उसकी सरफेस पे ही रिजाइड करेगा. चाहे आप शेल लो, शेल इज hollow from inside, there is nothing inside. Charge resides on its outer surface. But if you have a sphere, even if you have a solid sphere and it is conducting, even then there is no charge inside the sphere. Or pura charge, whole charge resides on the outer surface of the solid conducting sphere only. But for solid non-conducting sphere, we have charge inside the sphere as well. There we have electric field intensity. There we can find electric field intensity. Okay, a point charge causes an electric flux of this to pass through a spherical Gaussian surface of radius 10 centimeters centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface and what is the value of point charge? This is question number 19. This is your NCERT question, question number 19. So we have a point charge here. We have a point charge here and it produces, this charge produces an electric flux. Electric flux produced by this charge is given. Okay, so this charge produces an electric flux of -1 into 10 raised to the power 3 Newton meter square per coulomb. Okay, radius of this surface is given, Gaussian surface is given, it is 10 centimeters. So we can write this into its SI unit, it's 10 to the power -1 meter. If the question is, if the radius of the Gaussian surface were doubled, how much flux would pass through the surface? So if we increase the size of Gaussian surface, if we increase the radius of Gaussian surface, then will there be any change in electric flux? This is your question. Give me the answer. No. It depends upon the charge enclosed. It does not depend upon the size of Gaussian surface we are taking. It only depends upon the, as it depends upon charge enclosed only. Okay, because your phi E is Q upon epsilon naught. Yes? So electric flux depends upon charge enclosed. So if the radius of the Gaussian surface were doubled, there will be no change in the electric flux. Second question is, what is the value of point charge? How will you find the value of point charge? Electric flux is Q upon epsilon naught. And therefore, Q is equal to electric flux into epsilon naught. You simply have to put the values here. Put the value of electric flux first. It is -1 into 10 to the power 3. And value of permittivity of free space, it is 8.85 into 10 to the power -12. Okay. What will you get? Yes, it's -8.85 into 10 raised to the power -9 coulombs. So this is the answer. 8 बजे मॉर्निंग
हमें लग रहा है सर ने गलती से भेज दिया है.
चलो पूछ लेना, अभी बाद में डिस्कस करना. electric field due to a uniformly charged infinite plane sheet. So we have long infinite plane sheet. Infinite means never ending. And we have to find electric field intensity due to this. And so we will draw like this. It shows that it is extended from both the directions. Okay. So it is uniformly charged. It is uniformly charged. Okay. Uniformly charged means charges evenly distributed. Okay. So for this kind of sheet, we can consider a cylindrical Gaussian surface. For this kind of sheet, we can consider a cylindrical Gaussian surface. Okay. Let's draw a cylinder which passes through the sheet. Like this. Okay. Now, if we consider a small area element here, then what would be the direction of this area element? Perpendicularly upward. If we consider the small area element here, then n cap will point outwards. And if we consider area element here, then n cap will point in this direction. If we have our area element here, then n cap will point in this direction, perpendicularly downwards. For at the edges, n cap is pointing in outward, and here also it is outward. Okay. Because we have this positive charge here, so what should be the direction of electric field? Direction of electric field is outward. Outward, away from the positive charge. So this is the direction of electric field. Okay. Let sigma be the surface charge density. Sigma is the surface charge density. Now we are going to find electric field density at any point P here, which is at a distance R from the sheet. So at the edges, this electric field, you can see it is parallel to the area vector. Both the electric field intensity and area vector, they are pointing in the same direction. Okay. At the edges, they both are pointing in the same direction. So electric flux at the edges will be E and ds. EDS, and we have two different edges here, two edges here. So electric flux at the edges is 2 EDS. Okay. Now on the curved surface of the cylinder. On the curved surface of the cylinder. On the curved surface of the cylinder, electric field intensity is perpendicular to area vector. You can see area vector is pointing outward and electric field is pointing in this direction. So vector E and n cap, they are perpendicular to each other on the curved surface. So electric flux on the curved surface will be 0. Similar type of problem we had done in case of line charge distribution, but there electric field intensity we had found out because of the curved surface, not the edges. Because at the edges, their electric field intensity was 0. But here in this case, we have electric field intensity present at the edges, but there is no electric field intensity due to this on the curved surface. Opposite है उसका, ठीक है? So, and therefore total electric flux will be total electric flux is equal to 2ds. Also, electric flux is, according to Gauss's law, it is 1 upon epsilon naught times the total charge contained inside S. And this Q can be written as sigma ds. Because we are considering small area element. Na? So for small area element, we have this electric flux. So here also we'll consider for small area element only. Okay. So on comparing these two, we can write the expression for E. ds cancel ho jayenge hamare. So E is sigma upon 2 epsilon naught. Now enclose this in a box. ये क्या था क्वेश्चन पूछा? मम्मी मम्मी तो पूछ सकती है उनको बोलो 3 बजे तक, ठीक है? Now we will draw the graph. ग्राफ किसका ड्रॉ करेंगे हम? E versus R. Does this electric field intensity depend on the distance from the infinite plane sheet? No, it does not depend on R. It only depends on its own surface charge density. Yes, it only depends on sigma, its surface charge density. And epsilon naught is a constant. It does not depend on R. If we want to draw a graph, then how will we draw? How will we draw the graph? E is constant for any value of R. Where is E? On y-axis. It seems constant here, na? You can see this line is parallel, na? So E is constant. For any value of R, we'll have the same value of electric field intensity. Okay? चाहे आप अपना cylinder यहाँ तक बनाओ, cylinder यहाँ तक बनाओ. You can choose this point P anywhere, na? You can take this point P here or anywhere. So if we increase or decrease the distance, it will not affect the electric field intensity due to this infinite plane sheet. Electric field intensity depends on its surface charge density, not on R. Okay. Should I clear the screen? Next, we have questions based on it. Electric field intensity at a point due to uniformly charged infinite plane sheet is directly proportional to the distance, inversely proportional to the distance, independent of the distance, directly proportional. बहुत बढ़िया. ऐसे जो आंसर देते हो ना क्वेश्चन से पहले, बस लगता है बस अब आ गया. For a uniformly charged plane sheet, the electric intensity at a point is it's sigma upon 2 epsilon naught. Electric field due to two thin uniformly charged infinite plane sheets. इसमें we will take two infinite plane sheets. Okay. This is first plane sheet and this is second. Charge is distributed uniformly. These are placed parallel to each other. Okay. This derivation is very important. Okay. So we have two infinite plane sheets and we have placed these sheets parallel to each other. Surface charge density is different. Let sigma 1 be the surface charge density of first sheet and sigma 2 be the surface charge density of second sheet. So you can see that we have here three different reasons. This is reason 1, this is reason 2, and this is reason 3. Now we are going to find electric field intensity in these three reasons. So we'll take a sign convention here. Okay, let's consider this direction as positive and this direction as negative. It is going towards negative x-axis and it is going towards positive x-axis. Accordingly, we have chosen the direction signs. Okay. So due to this first sheet, you can see, let the electric field intensity due to this sheet be E1 and electric field intensity due to this sheet be E2. So we can write E1 as, what is the formula? For a plain sheet of charge, we have the formula sigma upon up to epsilon naught. So for first plain sheet, its surface charge density is sigma 1. Electric field intensity is E1. So we can write E1 as sigma 1 upon 2 epsilon naught. Similarly, for the second sheet, we can write E2 as sigma 2 upon 2 epsilon naught. Any doubt? And we know that for a positive charge, electric field is always away from the positive charge. It acts away from the positive charge always. This is the direction of electric field intensity. Okay. Now in reason 1, so what should be the direction of E1? Away from positive? Away from this, no, this plate. So E1 will point in this direction. So is E2, because E2 is also the electric field intensity due to positive charge. So it will point away from this charge. In the second reason, what should be the direction of E1? Away from this sheet 1. Yes, Aditya थक गया. E1 का डायरेक्शन क्या होगा ये? Away from this sheet. And E2 का डायरेक्शन उसकी शीट से दूर. When we talk about E2, we consider second sheet, not the first. Okay. So for this sheet, what should be the direction of E2? Towards E1. And here in the third reason, E1 will point in this direction and E2 will point in the same direction where E1 is pointing. They are pointing in the same direction. Okay. So now we are going to find electric field intensity in these three reasons one by one. In reason 1, net electric field is equal to, they both are pointing, yes, in the negative direction, right? So we can take minus E1 and minus E2. Put the values. It's minus sigma 1 upon 2 epsilon naught minus sigma 2 upon 2 epsilon naught. So this, we can take this minus 1 upon 2 epsilon naught. Outside in the bracket, we will have sigma 1 plus sigma 2. Okay. Similarly, for reason 2, we can write in reason 2, what will be right? E2. So E2 is, E1 is positive and E2 is negative here in the second reason because it is pointing in this direction. Towards positive direction, it is pointing towards negative direction. So E2, E1 minus E2. Now put the values. It's very easy, na? It's sigma 1 upon 2 epsilon naught minus sigma 2 upon 2 epsilon naught. Again, we can take this outside 1 upon 2 epsilon naught in the bracket. We'll have sigma 1 minus sigma 2. This is the electric field intensity in reason 2. Similarly, we can find for reason 3. In reason 3, both are very nice. Both are positive. So in reason 3, both are positive. Both E1 and E2 are positive. So it is sigma 1 upon 2 epsilon naught plus sigma 2 upon 2 epsilon naught, we can take 1 upon 2 epsilon naught outside common, and in the bracket we'll have sigma 1 plus sigma 2. Okay. By convention, here we have taken left to right positive, and right to left negative. We can choose any convention. As per our convenience, we can choose. How was the derivation?